Hello and welcome to the Screencast where we will introduce the properties of the arccosine function. Let g be the function whose domain is all t values between 0 and pi inclusive and whose outputs are determined by g of t equals cosine of t. We see in this graph that the cosine function is the dotted graph and g of t is only the solid piece of the graph. Note well, because it has a different domain, g is not the cosine function. Also of importance, notice that because the cosine function is periodic, it does not pass the horizontal line test, and thus the cosine function on its full domain does not have an inverse function. However, the graph of g, which is the cosine function with a restricted domain between 0 and pi, does pass the horizontal line test. That means we can consider an inverse function for the cosine function with a restricted domain. Looking at the graph of the restricted version of the cosine function as defined above, we see that the domain is all values of t such that t is in between 0 and pi inclusive, and that the range is all y values such that y is between -1 and 1 inclusive. In our previous study of inverse functions, we learned that their inputs and outputs are reversed. As a result, the domain of the inverse of the restricted cosine function is -1, 1, and the range is 0 to pi. Both intervals are inclusive. The restricted version of the cosine function we saw in the previous slide has an inverse function that we call the arccosine function. We formally define the arccosine function this way. Let y equal g of t equal the cosine of t be defined on the domain from 0 to pi inclusive, and observe that g takes inputs, which are angles between 0 and pi, and pairs them with outputs, which are x-coordinates on the unit circle, between -1 and 1. And for any real number y that satisfies -1 less than or equal to y less than or equal to 1, the arccosine of y is the angle t satisfying that t is between 0 and pi inclusive, such that the cosine of t equals y. We should remember that the cosine of t equals y has t as an angle, and y actually represents the corresponding x-coordinate on the unit circle. That means we can also write t equals the arccosine of y. Notice that means the output of the arccosine function is t, an angle. In addition, recall that in the context of the unit circle, an angle measured in radians equals the corresponding arc length. This is why we use the arc in arcsine. Given a value between -1 and 1, the arccosine function produces the corresponding arc, measured counterclockwise from 1 to 0, such that the cosine of that arc is y. Because the arccosine function is the inverse of the restricted cosine function, all the properties of inverse functions we previously learned will be true. For example, recall that an inverse function reverses the process of the original function, and that y equals g of t and t equals g inverse of y say the same thing from different perspectives. We know that y equals the cosine of t means that y is the cosine of the angle t. Changing perspective and writing the equivalent statements, t equals the arccosine of y, or t equals the inverse cosine of y, means that t is the angle whose cosine is y. Another property of inverse functions we learned previously is that any point AB that lies on the graph of g of t equals y corresponds to the point B, A that lies on t equals g inverse of y. For example, we know that pi over 2, 0 lies on the graph of the restricted cosine function. And so then 0, pi over 2 lies on the inverse cosine function. And using function notation, we can say the cosine of pi over 2 equals 0, which means 0 is the cosine of the angle pi over 2. And switching perspective, we can also say that pi over 2 equals the arc cosine of 0, or pi over 2 equals the inverse cosine of 0, both of which mean pi over 2 is the angle whose cosine is 0. Later, we will practice evaluating the arc cosine function, always keeping in mind that the arc cosine function is defined in relation to the restricted domain 0 to pi of the cosine function.